For this next lesson in curve sketching, we're going to take a look at the vertical asymptotes. So, in this chapter, we're going to be graphing functions without the aid of a graphing calculator. Rather, we're going to be analyzing curves using the principles of calculus instead. We may use our graphing calculator to illustrate certain features of curves. However, we must be able to sketch curves manually. So remember, when you take this into your test, you're not going to have the graphing calculator to verify. When we do the practice, you can, but for the test, you have to be able to do it manually using the principles of calculus. Each curve will be analyzed with respect to the following checklist. The checklist is intended as a guide when sketching a curve by hand, and it will provide us with the information we need to make a sketch that displays the most important aspects of a function. Now, you're not going to have to illustrate every single point, but these are the key characteristics that help us properly do our curve sketches. So, we have our domain, intercepts, symmetry, asymptotes, intervals of increase and decrease, local maximum or minimum values, concavity and points of inflection, and then actually sketching the curve. Now, we know that the domain, the intercepts, and the asymptotes were all things that we learned how to do in 20-1 and 30-1. We will review it, but we learned how to do it in 20-1 and 30-1. The symmetry we talked about in the last lesson. The intervals of increase and decrease, and the local maximum or minimum values we talked about in the last chapter in chapter 4. And the concavity and points of inflection, as well as doing the proper curve sketching, are things that we're building up towards within this chapter. We know when we talk about the domain of x for which the function f of x is defined is just helping us know every possible value we can have. It will help us with our vertical asymptotes. It will help us with points of discontinuity to help us graph out the key aspects of our graph. We know that polynomial functions have a domain of all real numbers and are continuous functions. So a polynomial function is going to be differentiable everywhere. For our rational functions, they may have a restriction on x as the denominator cannot equal 0. Now remember, that doesn't mean that it will always have a restriction on x. It's just a possibility that we need to check for. So given this function, y is equal to 1 over x plus 4. If y is equal to 1 over x plus 4, and our denominator can't equal 0, then that means that x plus 4 can't equal 0, or x cannot equal negative 4. So we'd state for our domain that x cannot equal negative 4, where XER, or if you prefer, x is an element of negative infinity to negative 4, or negative 4 to positive infinity. We know that this is going to have a vertical asymptote at negative 4. And it also is going to have a horizontal asymptote at y is equal to 0. This one is not going to have an x-intercept because of that horizontal asymptote. It is going to have a y-intercept at y is equal to 1 over 4 when we make x 0. And then it's going to look something like this. When we have square root functions, if we take the square root of something, it can't have a negative radicand. So there may possibly be a restriction on x. Once again, doesn't mean there's always a restriction on x, but it's certainly a possibility. So if I consider the function y is equal to the square root of x minus 3, then I know that x minus 3 has to be greater than or equal to 0 for this to be possible, which means that x would have to be greater than or equal to positive 3, and x would also have to be a real number. Or if you prefer, x is an element of 3 to infinity. In this case, the x-intercept is going to occur when x is equal to 3. The y-intercept does not actually exist because of that restricted domain where x has to be greater than or equal to 3, which means that x can't equal 0, so there would be no y-intercept. And I'm going to get a graph that looks something like this. For example 1, for the first piece, we need to be able to state the domain of each of the functions without graphing it out, because graphing and the curve sketching is going to be our last part when we actually do this. So if I'm given a polynomial function like this, then we know for a polynomial function, the domain is going to be xer. If I'm given a rational function, then the domain is going to be restricted based on that denominator where it can't equal 0. So I can say that the domain is going to be built upon the fact that x minus 3 cannot equal 0, which means that x could not equal 3. When I get to example C, we can see this rational exponent, which means that this would be a radical function, but because the denominator is 3, which means the index would be a 3, I can take positive and negative cube roots. I just can't take positive and negative square roots and fourth roots and sixth roots. So in this case, I am going to have a domain of xer. Whereas when I get to example D, this is a square root, which means that my domain is going to be based on the fact that 9 minus x squared has to be greater than or equal to 0. Or negative x squared plus 9 has to be greater than or equal to 0. I'm going to divide both sides by negative 1. To get x squared minus 9 has to be less than or equal to 0. Don't forget, when we divide by a negative, it changes the direction of the inequality. And the factored form of this would be x plus 3 and x minus 3 has to be less than or equal to 0, which would give me a domain where negative 3 has to be less than or equal to x, which has to be less than or equal to 3. For example E, once again, it is a square root, So 4 minus x would have to be greater than or equal to 0. Negative x would have to be greater than or equal to -4. And when I divide by -1, change the direction, and x has to be less than or equal to 4. For example F, it is a radical with an even index, but it is also in the denominator, meaning that the root from the denominator, x, cannot equal 3. So I would have to start by stating that x minus 3 has to be just greater than 0, not greater than or equal to 0, which means that for this domain, x has to be greater than 3. And last but not least for g, we see that we have a radical here with an index of 2, which means that for our domain, 3x minus 2 has to be greater than or equal to 0 because it's not in the denominator. 3x would have to be greater than or equal to 2, and x would have to be greater than or equal to 2 over 3.